In this video, we will be covering Napoleon's theorem. It is presented by Tran, which is me, Winston Lin, and Caleb Huning from the course Math 3321, Section 501 at the University of Texas at Dallas. So, suppose we are given any random triangle. We're going to construct 3 equilateral triangles on each side of this random triangle. The centroids of the equilateral triangles form another equilateral triangle, and this is called Napoleon's theorem. Here we have an obtuse triangle on the left side and an isosceles triangle on the right. We'll make equilateral triangles on each side of the obtuse triangle, and then we'll draw the centroids of each equilateral triangle. Notice that we get another equilateral triangle from these centroids. Similarly, the theorem would hold for the isosceles triangle on the right. In fact, you could give me any type of triangle and this theorem would hold, whether it be an isosceles triangle, an obtuse triangle, or any other type of triangle. Now, the theorem was named after Napoleon Bonaparte. Here we have a very famous painting of Napoleon, which you might have recognized. The title of the painting is Napoleon Crossing the Alps, and Napoleon was a military leader and the Emperor of France from 1804 to 1814. He ultimately passed away in 1821. However, the earliest known publication of Napoleon's theorem was in 1825, which was 4 years after he passed away. Many people believe that Napoleon Bonaparte himself discovered the theorem, and funnily enough, he didn't even prove the theorem, so it wasn't even named by the person who discovered it first. Luckily for us, we will be getting to the proof of the theorem. In fact, we'll be doing 2 different types of proofs for Napoleon's theorem. Winston will be doing the first proof, and Caleb will be doing the second one. But we're going to have to prove a few things first that we'll have to use later on when proving Napoleon's theorem. We'll be proving the Pythagorean theorem, the law of cosines, the law of sines, and the fact that the 3 medians of an arbitrary triangle intersect at its centroid, which lies 2/3 of the way along all 3 medians. The proof for these 4 facts may use congruent and similar triangles. For those that need a refresher on congruent and similar triangles, we will cover that towards the end of the video. Now, we'll first start out by proving the famous Pythagorean theorem. The Pythagorean theorem tells us that the square of the length of the hypotenuse of a right triangle is equal to the sum of the squares of the 2 other sides of the right triangle. Hence, we get a squared plus b squared equals c squared, where c is the length of the hypotenuse, which is the longest side in a right triangle, and a and b are the lengths of the 2 other sides of this triangle. There are several proofs of the Pythagorean theorem, but we'll only be going over one of them here. So let's say we're given a right triangle with sides A, B, and C, where C is the hypotenuse. We need to prove that a squared plus b squared equals c squared. We'll create 3 other copies of this right triangle by rotating the original right triangle by 90 degrees, 180 degrees, and 270 degrees. So we now have a small square-shaped hole with side C, as shown by the yellow square, and a big square with side A plus B, as shown by the red outline. Since the area of any triangle is 1/2 times the base times the height, we know that the area of one of the right triangles is 1/2 times AB. Meanwhile, the area of the bigger square with sides A plus B is A plus B squared, and the area of the square hole with side C is C squared. We also know that the area of the bigger square, as shown by the red outline, is equal to the area of the square hole summed with the area of the 4 right triangles. Using this fact, we can set the area of the bigger square to the area of the 4 triangles and the area of the square hole equal to each other. Hence, we have that a plus b squared, which is the area of the bigger square, is equal to 4 times 1/2 ab, which is the area of the 4 triangles, plus c squared. And this is the area of the square hole. We'll write out the binomial on the left side to get a plus b times a plus b, which equals 4 times ab divided by 2 plus c squared. Simplifying both sides of the equation gives us a squared plus ab plus b squared equals 2ab plus c squared. Now we'll combine like terms on the left side. So we'll get a squared plus 2ab plus b squared equals 2ab plus c squared. Lastly, we'll subtract 2ab from both sides of the equation, which leaves us with a squared plus b squared equals c squared. And this is the Pythagorean theorem. Next, we're going to prove the law of cosines. First, let us state the law of cosines. Given the lengths of two sides of a triangle and the angle between them, we can find the length of the third remaining side by the law of cosines. And this is given by the formula c squared equals a squared plus b squared minus 2ab times cosine c, where a, b, and c are the sides of any triangle, and the capital C is the angle between sides a and b. Notice that if we have a triangle with sides A, B, and C, where the angle between sides A and B is 90 degrees, then we would end up with the Pythagorean theorem. This is because the cosine of 90 degrees is 0, so we would be left with c squared equals a squared plus b squared. And so we know that the law of cosines works for right triangles at the very least. However, we'll need to prove that it works for any type of triangle, so we can use the law of cosines for our proof of Napoleon's theorem. To prove the law of cosines, we'll start out with triangle ABC, where BC equals A, CA equals B, and AB equals C. We want to show that C squared equals A squared plus B squared minus 2AB times cosine C. So we're going to draw height BD from vertex B to CA, and we'll let H equal BD, x equals CD, and y equal DA. And this gives us right triangles BCD and ABD. By definition, we know that cosine of C equals x divided by A, since the cosine of an angle of a right triangle is equal to the adjacent side, which is x in this case, divided by the hypotenuse, which is A. Next, we're going to multiply A to both sides of this equation, and we'll get x equals A times cosine of C. Using the Pythagorean theorem for triangle BDC, we know that x squared plus h squared equals a squared. We'll subtract x squared from both sides of this equation to get h squared equals a squared minus x squared. Again, we'll use the Pythagorean theorem for triangle ABD. And so we know that c squared equals y squared plus h squared. Notice that y equals side b minus x. And so we'll substitute y with b minus x to get b minus y squared plus h squared equals c squared. From earlier, we found that h squared equals a squared minus x squared. Substituting h squared with a squared minus x squared gives us b minus x squared plus a squared minus x squared equals c squared. Next, we'll write out the binomial on the right side. So we'll get c squared equals a squared minus x squared plus b squared minus 2bx plus x squared. Simplifying the right sides gives us c squared equals a squared plus b squared minus 2bx. From earlier, we found out that x equals a times cosine c. And so we'll substitute x with a times cosine c to get c squared equals a squared plus b squared minus 2ba times cosine c. And rearranging the right side gives us c squared equals a squared plus b squared minus 2ab times cosine c, which is the law of cosines. Now, we need to prove the three medians of an arbitrary triangle intersect at its centroids, which lies 2/3 of the way along all three of its medians. First, we'll need to define a few terms. The median of a triangle is a line segment from a vertex of the triangle to the midpoint of the opposite side. So a triangle is going to have three medians. And the centroid is the point where all three medians of a triangle intersect each other. Now that we have defined the median and centroid of a triangle, we can start our proof. So let's say we are given an arbitrary triangle, ABC. We'll draw median AX from vertex A to BC, and median BY from vertex B to AC. And we'll let G be the point where AX and BY intersect. So we want to show that AG equals 2 times GX for G to lie 2/3 of the way from vertex A to X, and that the three medians intersect at G. We'll first prove that AG equals 2 times GX. Now, we'll draw a line segment from x to y. So we have that angle ACB equals angle YCX. Now, because AX and BY are medians, CA is twice the length of CY, and CB is twice the length of CX. And so we have that CY divided by CA equals 1/2, and CX divided by CB also equals 1/2. And so we get that CY divided by CA equals CX divided by CB, which equals 1/2. And so we have that triangle YXC is similar to triangle ABC by side, angle, side. And so we get that CY divided by CA equals CX divided by CB, which equals XY divided by AB, which equals 1/2, since the lengths of corresponding sides of similar triangles are proportional. Now, focusing on XY divided by AB equals 1/2, we'll multiply both sides by 2AB, and this is going to give us AB equals 2XY. And so we'll get that AB divided by XY equals 2. So from earlier, we found out that AB is parallel to XY, and so we'll have pairs of alternate interior angles. And so angle BAG equals YXG, since transversal AX cuts through the parallel lines, and angle ABG equals angle XYG, since transversal BY also cuts through the parallel lines. And so triangle AGB is going to be similar to triangle XGY by angle. And since the lengths of corresponding sides of similar triangles are proportional, we have that AG divided by GX equals AB divided by XY, which equals GB divided by GY, which equals 2. Now we'll just focus on AG divided by GX equals 2. And so we'll multiply both sides by GX to get AG equals 2GX, which we were trying to prove. Hence, we just showed that two medians intersect at a point that is 2/3 of the way along one of those two medians. And so in our case, median BY intersects median AX at a point that lies 2/3 of the way from A to X. Next, we need to show that all three medians intersect at G. So if we were to draw median CZ from vertex C to AB, CZ would intersect AX at the point that would be 2/3 of the way from A to X, using the same method we just used to prove that AG equals 2GX. However, this point that lies 2/3 of the way from A to X is point G, and so CZ has to go through G. So then we have that G is a centroid, since all three medians go through G. And we have just proved that the three medians of an arbitrary triangle intersect at its centroid, which lies 2/3 of the way along all of its medians.
Here's a quick proof on the law of sines. From basic geometry, we know that the area of a triangle is 1/2 times the base times the height. This can be used to prove the law of sines, or that the sine of angle A over the side A is equal to the sine of angle B over side B, which is also equal to the sine of angle C over side C. First, let's create a triangle ABC and draw the altitude from A, that is a line perpendicular to the side that passes through vertex A. This will be the height of our triangle. According to the definition of the side of angle C, it is, in a right triangle, the opposite side to the angle over the hypotenuse, or the longest side of the triangle. Thus, sine of angle C is h1 over side B. We then approach from the other side of h1 to find that the sine of angle B is equal to h1 over side C. We rearrange the two such that B times sine of C is equal to h1, which is also equal to side C times the sine of angle B. And thus, with a little algebra, we find that the sine of angle C over side C is equal to the sine of angle B over side B. We draw another altitude, this time for our purposes, from angle C, to find that we can repeat the process for another side. In this instance, sine of angle A equals h3 over side B, and the sine of angle B equals h3 over side A. Therefore, side A times the sine of angle B is equal to h3, which is also equal to side B times the sine of angle A. And therefore, the sine of angle B over side B is equal to the sine of angle A over side A. So now we have that the sine of angle A over side A is equal to the sine of angle B over side B, which is also equal to the sine of angle C over side C, and thus the law of sines has been proven. For our application in the coming proof, we actually need to take a few steps backwards. So we've previously stated that the sine of angle C is equal to h1 over side B. With a little rearranging, this becomes B times sine C equals h1. Once again, the area of a triangle is 1/2 times the base times the height. Thus, the area of our triangle with A, side A as the base, and h1 as the height will be 1/2 times side A times side B times the sine of angle C. We repeat this process to find that the area of a triangle is also equivalent to 1/2 times side A times side C times the sine of angle B, as well as 1/2 times side B times side C times the sine of angle A. Now that we've established a few things, we can begin a trigonometric proof of Napoleon's theorem. To restate what Napoleon's theorem is that if equilateral triangles are constructed on each side of any given triangle, the centroids of those triangles will also form an equilateral triangle when connected. To begin, let us create line segments AI, AG, and give all of our relevant line segments names. So AG will be Q, AI will be P, GI will be GI, and we will also label the sides A, B, and C. Then, let's review the law of cosines. A squared equals B squared plus C squared minus 2 times B times C times the cosine of angle A. This translates into what we are looking for, line GI. It will translate to where line GI squared equals P squared plus Q squared minus 2PQ cosine angle GAI. We currently have 3 unknown angles within angle GAI, but we can figure out 2 of those angles to make our lives much easier. To do so, here's a close-up of triangle ABD. We know that triangle ABD is an equilateral triangle. We also know that the centroid G lies on all 3 medians, so we can extend line AG to become line AX. When we cut triangle ABD with line AX, since we know that AX is a median, and that triangle ABD is an equilateral triangle, we can apply relative measurements to the sides. Then, once we make note of the fact that all angles of an equilateral triangle are 60 degrees, we can see that triangle ABX and triangle ADX are congruent by SAS, or side angle side criteria. This means that angle alpha and its counterpart, angle DAX, must be equal, or rather, that angle alpha is half of angle DAB, which is 60 degrees by default as an angle of an equilateral triangle. Thus, angle alpha must be 30 degrees. We repeat this process with triangle ABD to determine that angle gamma is also 30 degrees. We then go back to the model and replace both angle alpha and angle gamma with 30 degrees. Then we take a look at our original formula, which was GI squared equals P squared plus Q squared minus 2PQ times the cosine of angle GAI. We can now replace angle GAI with angle BAC and our 2 new 30 degree angles. Thus, our new formula is GI squared equals P squared plus Q squared minus 2PQ cosine angle beta plus 60 degrees. From there, we can relate the lengths of P and Q to the lengths of B and C respectively to make things more universal. By using the Pythagorean theorem, the fact that the centroid lies 2/3 of the way down the median, and the fact that triangle ABD is an equilateral triangle, we can show the length of C in terms of the length of Q. According to the Pythagorean theorem, a squared plus b squared equals c squared. Well, in this case, we have L squared equals 3/2 times Q squared equals C squared. We already know that line Q, when extended to line DB, will cut it in half. Thus, our new line segment, L, will be equal to half of any equilateral side. We use this knowledge to relate to C, so our new formula looks like 1/2 of C quantity squared plus 3/2 times Q quantity squared equals C squared. And then we proceed to do a little of algebra to end up with the fact that Q equals C over the square root of 3. And then we can do it again for P and B, starting with the formula m squared plus 3/2 times P squared equals B squared. And then we have the algebra again. Now we can go back to our formula, which was gi squared equals p squared plus q squared minus 2pq cosine beta plus 60 degrees. Once we substitute what we now know in, it becomes gi squared equals b squared over 3 plus c squared over 3 minus 2/3 times bc cosine beta plus 60 degrees. Or we could say that 3 times gi squared equals b squared plus c squared minus 2bc cosine angle b plus 60 degrees. Next, we will break down angle beta plus 60 degrees, or the cosine of that quantity. To break down the cosine of angle beta plus 60 degrees, we'll need to do trigonometric identities. Unfortunately, or fortunately, this video is only meant to teach you a few tricks and applications in geometry, so it will give you the trigonometric identities that you need to work this out. The one we need to break down the cosine of angle beta plus 60 degrees is the cosine of x plus y equals the cosine of x times the cosine of y minus the sine of x times the sine of y. When we apply this to the cosine of angle beta plus 60 degrees, we get that it equals the cosine of beta times cosine of 60 degrees minus the sine of beta times the sine of 60 degrees. It turns out that cosine of 60 degrees and the sine of 60 degrees have actual values, so we can substitute those in to get our final equation, which is the cosine of beta over 2 minus the square root of 3 over 2 times the sine of beta. We'll then substitute this in as well to our formula to obtain 3 times gi squared equals b squared plus c squared minus bc times cosine of beta plus the square root of 3 times bc times the sine of beta. And then we go back to break down the sine of beta and the cosine of beta finally. For the next two identities, we'll return to the base triangle of ABC. We apply the law of cosines to this triangle, which states that a squared equals b squared plus c squared minus 2bc cosine of a. From this, we can arrange the letters and numbers to isolate bc cosine of a, so that 1/2 of a squared minus b squared minus c squared equals negative bc cosine a. And we'll stop here and go to the other side. We then apply the law of sines, which states that 2 times the area of triangle ABC is equal to BC sine of A. In our case, angle A here is equivalent to the angle of beta that we were using. Now, we'll put all the pieces back together and then substitute what we just learned back in. So now, 3 times gi squared equals b squared plus c squared plus a squared minus b squared minus c squared over 2 plus the square root of 3 times 2 times the area of the triangle ABC. And this might seem complicated, but this is fine. We'll stop here and we'll try to replicate the process with the other two sides of our theoretically equilateral triangle. Now, this is the exact same process, so I'll be going a little faster than before. So hi squared equals t squared plus u squared minus 2tu times the cosine of angle beta plus two 30-degree angles, or 60 degrees, by the law of cosines. Then we have t equals a over the square root of 3, and u equals b over the square root of 3, by the Pythagorean theorem and our previously mentioned relationship between the centroid and the median. So we get that hi squared equals a squared plus b squared minus 2ab times the cosine of angle beta plus 60 degrees. Cosine of angle beta plus 60 will equal the cosine of beta over 2 minus the square root of 3 over 2 times the sine of angle beta by substituting trigonometric identities. Then we substitute that in to get 3 times hi squared equals a squared plus b squared minus ab cosine beta plus the square root of 3 times the ab times sine beta. And this equals the negative a squared minus b squared plus c squared over 2 equals negative ab cosine beta, and then 2 times the area of triangle ABC equals ab sine beta by the laws of sines and cosines. And so when we substitute this back in, we get that 3 times hi squared is equal to a squared plus b squared plus c squared quantity over 2 plus 2 times the square root of 3 times the area of triangle ABC. Now you might notice that these two quantities that we've calculated are in fact equal, and that's the point behind the proof, that we prove that each of these lines is equal to a squared plus b squared plus c squared over 2, quantity over 2, plus 2 times the square root of 3 times the area of ABC. Now the third side will yield the same results, that our last line, gh, 3 times gh squared, will also equal a squared plus b squared plus c squared all over 2, plus 2 times the square root of 3 times the area of triangle ABC. But I will not be walking through that one. I've created a diagram and put it here, so if you want to try it yourself, you can pause the video. So in conclusion, now that we've proved that all three sides are equal to this quantity, you can say that triangle GHI fits the definition of an equilateral, or equal sides, triangle. And that concludes the proof, the trigonometric proof of Napoleon's theorem.
Now that we've shown Napoleon's theorem to be true, let's see an alternate proof which uses an argument by rotational symmetry. We'll begin with triangle ABC and construct equilateral triangles on each of its sides as before. Here we have triangle AEC constructed on side AC, CDB constructed on BC, and BFA constructed on AB. Points H, I, and J are placed on the centroids of these triangles. Our goal, as the theorem says, is to show that triangle HIJ is equilateral. We will first rotate the entire figure about point J by 120 degrees. This gives us a new copy of triangle ABC, as well as copies of the other two equilateral triangles, and a copy of HIJ, which is H'I''J. Each rotated copy is congruent to the original. We would like to show that angle D'AE is equal in measure to angle BCA. First, let's observe that the angles around a point add up to 360 degrees, so the sum of angles around point A is 360 degrees. We also know that triangle ABC is congruent to triangle FC'A, so angle CAB is equal to angle C'FA, and angle C'AF is equal to angle CBA. Since triangles D'C', C'A, AEC, and AFB are all equilateral, we know that angles D'Ac', EAC, and FAB are all equal to 60 degrees. We can take the sum of all angles around point A to be equal to 360 degrees, and subtract those that are equal to 60 degrees to get the sum of angles D'AE, C'AF, and CAB to be equal to 180 degrees. We can substitute C'AF for ABC, since we know that they are equal. The sum of a triangle's angles is equal to 180 degrees, so in triangle ABC, we can write the sum of angles CAB, ABC, and BCA to be equal to 180 degrees. Now we have two equations equal to 180 degrees, so we can set them equal to each other, and subtract CAB and ABC to conclude that angle D'AE is equal in measure to BCA. Now, let's draw a line between points D' and E. Triangle AEC is equilateral, and triangle C'D'A is equilateral and congruent to triangle BDC. So from this, we can know that line segment D'A is equal in length to line segment BC, and likewise AE is equal to AC. From this, we can conclude that triangle ED'A is congruent to ABC by the side angle side criteria. Now let's consider the position of points H' and I relative to this triangle. They are the centroids of the equilateral triangles constructed on two sides of triangle ED'A. Looking now at points H and I, they are in the same position relative to triangle ABC, which is congruent. From this, we may argue that the distance between H' and I is equal to that between H and I, and the same argument may be made for a segment H'I'. We can look at the centroids of a different pair of equilateral triangles to draw a similar conclusion that line segments I'J and Ij have equal length, and that H'J and Hj have equal length. Now let's rotate the whole figure once more by 120 degrees. Connecting points H and I with their rotated copies gives us the hexagon HI, H'I', H'I'. From before, we know that the sides of this hexagon have equal length, and the 6 triangles composing it which meet at point J have equal side lengths. Each of these triangles must then be congruent by the side-side-side criteria. We also know that the angles around point J sum to 360 degrees. Since the 6 triangles meeting at this point are congruent, these 6 angles have equal measure. So to find the measure of one of those angles, such as angle IJH, we divide 360 degrees by 6 to get 60 degrees. Now let's consider that instead of rotating the original figure around point J, we could have instead rotated it around point I or point H. This would have given us the same hexagon centered on point I or point H rather than point J. We can use this to argue that each of the 3 angles of triangle HIJ is equal to 60 degrees. Thus, triangle HIJ is equiangular. Now let's prove that an equiangular triangle is also equilateral. Begin with triangle ABC, which we suppose has 3 equal angles. Draw an altitude from any of the 3 vertices. In this example, we draw altitude CX. Draw an altitude from any of the 3 vertices. In this example, we draw altitude CX. Now we have 2 triangles, ACX and BCX, which have one set of 60-degree angles, one set of 90-degree angles, and a common side. So triangle ACX is congruent to BCX by side angle criteria. We know then that side AC is equal to side BC. Repeating that process for either of the remaining altitudes, we can show that all 3 sides of this triangle have equal length, and thus the triangle is equilateral. Back to the original figure, we know now that triangle HIJ has 3 equal angles, and so it must be equilateral, which completes our second proof of Napoleon's theorem. Now let's briefly explain the ideas of similarity and congruence, which we have used at several different points in our proof of Napoleon's theorem. 2 triangles are congruent if they have the same size and shape, meaning all of their side lengths and angle measures correspond. We can show that triangles are congruent if there exists a rigid transformation, which causes one triangle to coincide with the other. There are 4 different criteria we can use to show that triangles are congruent. These are side-side-side, side-angle-side, side-angle-angle, and angle-side-angle. If we know any of these are equal for 2 triangles, then they are congruent. These congruence criteria were first proved by Euclid, derived from his postulates. We will explain each of them here, but we will not provide rigorous proofs. First, the side-side-side criteria. This tells us that if all three corresponding sides of a triangle are of equal length, then the triangles are congruent. Next, the side-angle-side criteria. In this scenario, we know two sides of a triangle and the angle bounded by them is equal to that of another triangle, which this criteria tells us is congruent. Next, the side-angle-angle criteria. We know that the angles of a triangle have the sum 180 degrees. If you know two angles of a triangle, then you can calculate the third angle of the triangle. Knowing the three angles of a triangle defines its shape, and then knowing one of the side lengths between two of those angles gives the triangle its size, thus defining a unique triangle. Similar to side-angle-angle criteria, the angle-side-angle criteria tells us two angles and one side between them. If this is equal for two triangles, then they are congruent. Next, similarity is a similar concept to congruence, except similar triangles only have the same shape, but not necessarily the same size. If two triangles are similar, that tells us that their angles are equal and the ratio between each of their sides is equal, called a scale factor. For example, if we know triangles DEF and ABC are similar with a scale factor of 0.4, and side AB has length 1, then side DE's length is given by AB times 0.4, which is 0.4. Similar to congruence, there are useful criteria we can use that two triangles are similar. These are angle-angle, side-angle-side, and side-side-side. We know that two triangles are similar if all three of their angles correspond, but we also know that the angles of a triangle sum to 180 degrees, so with two angles of a triangle we can always find the third. Thus, knowing two angles of two triangles correspond is sufficient to prove that they are similar. Next, the side-angle-side criteria for similarity. Unlike with congruence criteria, this does not tell us that corresponding sides have equal length, but rather that they have equal ratios. This criteria tells us that if the angle between two of those sides is equal, then the triangles are similar. Likewise, the side-side-side criteria tells us that if all three sides of each triangle have an equal scale factor, then the triangles are similar. Thank you for watching. Here are references used in the creation of this video.